Yeah, actually the title has changed, sorry. Actually I have a lot of time. Today I will talk something more. I will talk spin pumping, spin seeback, and SMR in this kind of antiferromagnet related sandwich structures. So actually, so there is a lot of people talking about antiferromagnet spintronics these days. I think I don't have to introduce too much. So these guys show that you can have a kind of memory effect with the AIMR effect in conducting antiferromagnet, and actually the work very important for the spintronic community is because it shows that we can really make antiferromagnet into some device. So the device is kind of sexy things for the industry. So maybe it can really be useful someday. And also for the insulators, so there are also progress. So this pioneering work is from Ohio State University, and they show they can do spin pumping in the platinum bilayer, and they compare this kind of signal with the signal from the trilayer system with a nickel oxide interlayer. So they even find that the spin pumping can be further enhanced even you have this additional layer of antiferromagnet. And also very important work also is from Moriyama-san, is showing that even you grow this material into 10 nanometer, the transparency is still 0.8, which means that this material really very good for spin current transmission. And from Ohio State also just have a lot of other testing of all the material. So we can see that not everyone is very good for spin current transmission. So some material pretty short. But all of these works show that you can pass spin in antiferromagnet insulators. So this actually opens the possibility to further explore in this kind of insulating antiferromagnet direction. So now actually I want to give some comment to myself. So as you can see, I'm not a kind of a young leader. I'm just a very young, humble follower of these kind of works. Because actually in 2015, 2 years ago, actually we have very few ideas we can do upon this kind of a pioneering work. But later on, actually, we have some close look at the data. So we find that if we look at the spin injection in this kind of a structure, so actually you can subtractly imagine that it's just the flow of angular momentum just goes through this antiferromagnet. And this kind of process is pretty similar to the neutron scattering. So actually we draw these two cartoons just by putting some balls, just mimicking the neutron. So actually and for neutron scattering, actually we pretty sure that we can probe spin fluctuation and determine orbital temperature with these kind of particles. So since that looks quite similar, so we kind of guess that the spin current can also kind of probe the magnetic fluctuation, the dynamics in the antiferromagnet a little bit. If we look at closely, we will find that this kind of structure is very easy. This kind of spin injection very easily just realized by the spin pumping as the spin source and the inverse spin Hall effect as the spin detector. And we just mimic the others, make this kind of trilayer samples, which is look like this. And now actually we still look at the same data, but because we have some kind of a subjective guess, so we believe that some fluctuation of spin is already kind of included in this kind of signal. So actually the most straightforward thing to check this kind of guess is to make a temperature-dependent measurement. So here is our sample. It consists of a platinum layer, a cobalt oxide layer, and an YIG. As you can see this TEM image, so I think the orientation of cobalt oxide is 001, and you can see kind of good layers stacking and the platinum ions. And actually, I want to talk to Felix. I think our interface is pretty good here, right? Okay, here is Yeah, but it's very important according to Felix yesterday. So here is kind of a very common spin pumping data. So at 150 Kelvin. So we have the spin absorption, the microwave absorption at some point, FMR point, and the corresponding inverse spin Hall effect. When you see this, you know that you already have spin injection due to FMR. And we can do the temperature sweep in our PPMS system. And you can see that the absorption does not vary much, but it does have some temperature dependence. But if you look at the temperature dependence of the inverse spin Hall effect, you will find that it's very obviously it's not monotonic. So you have a very kind of small value at room temperature. So if you go down, it suddenly goes kind of big, and if you go down further, it turns small, and finally it vanishes at 10 Kelvin. So we just extract this kind of peak position and plot it here. So it looks like something like this. So it's obviously it's a peak, right? And we also double check the structure without this carboxide layer. So it's just monotonically goes down. So maybe actually there is some argument of why it goes down like this, but obviously there is no peak. So actually the problem for us then is that to explain why there is a peak here. But actually if you look at the literature of the accessibility of carboxide, so like by the Charlie Chen group, like almost more than 20 years ago, so actually they show that for carboxide thin film, if you change the thickness, you can see this kind of peak position around the new temperature of it, and it will increase with the carboxide thickness. So actually, at the time, we kind of naively think that this point should be the new point. But the first check, very easy, is that we can check the thickness dependence. So we do just prepare different thickness of carboxide, and we see it does this peak position does shift it to high temperature when we increase the thickness of carboxide. So maybe it indicates something. Maybe it's kind of it's a really new temperature, and also we continue to look at this kind of behavior in the structure. We put nickel oxide instead of carboxide. So basically, this kind of behavior looks pretty universal, at least for these two systems. And actually, we can also see the spin feedback factor when we do spin pumping, because if you put microwave on a sample, actually you effectively heat the platinum layer a little bit. So actually they automatically give you a temperature gradient across the z direction. And if you zoom in this kind of very small area, and you will see the spin feedback fact. And you can extract the spin feedback value and plot it against the temperature. You will see that the behavior is nearly the same with the data from spin pumping. So the final thing actually we need to see is that to tell whether it's really new temperature or not, because it's can only we can argue, we can kind of speculate it's maybe new temperature because everything looks like the new temperature behavior, but actually we need kind of a very hardcore evidence to pin down this. So to do this, actually we go to XMLD in UC Berkeley. And so in the experiment, actually, we can directly use the X-ray linear polarized light to illuminate our sample and to try to get this kind of XMLD contrast. So actually, so the red and black curve represents the spectrum we get from the linear polarized light perpendicular and parallel to this magnetization of YIG. So actually, we can see that it's really have some finite contrast. So our collaborator just plot this kind of difference against the temperature. So finally, he's find that the new temperature is something here, and we plot and we just compare this one to our data. So it's a pretty good kind of agreement. So by this, actually, we think we can ambiguously say that this peak is somehow very close or just right at the new temperature. So actually, with this work actually does tell you that spin current is somehow can serve as a probe of the new order of the system. So if you want to know the new order of your sample, you just put it on some YIG or some ferromagnet and detect the spin pumping signal. Somehow it will give you the result. What is funny is that before the experiment, I think no theorist think, at least tell that it's possible like this. But after some experiment, like I will show later, so basically have the same behavior. So many theorists begin to say, oh, it's kind of obvious. So you should have some maximized transformation around new point. Yeah. So actually, there is some similar work appear at the same time. Is the one from is done by Flango, the girl in France group. So she actually managed to show that if you look at the damping constant, so this will tell you how much spin actually has been pumped out of his ferromagnet. And here he used iron manganese as a antiferromagnet layer, and he also sees some anomaly enhancement of this kind of line width. So actually is this basically of the same physics with us, and also the paper mentioned by Moriyama-san just now, and this kind of spin seeback effect. So it's a thermal way of injection of the spin. So basically it tells you the same story. But actually I kindly suggest Moriyama-san to cite us at the same time with this paper. Okay, so next it's after that work, actually we kind of think what's the next to do. And we just look at this kind of table, and we find that of course for the bilayer platinum YIG structure, we have already done spin pumping, spin seeback, spin SMR. So, but actually for this kind of antiferromagnet sandwich trilayer device, so there is SMR is still missing. So at that time, we think this kind of work will be pretty trivial. We just make it up and publish some small paper, and that's everything. But actually, we didn't expect that there is some maze waiting for us. So of course, you know the tricks of this kind of thing from Felix yesterday. But today, I will show that actually our explanation is not so obvious at least from the very beginning. So this is SMR. So I think I don't have to say that again. So basically, it tells you that if you put some material with spin hole and on YIG or other ferromagnet, so you can have this kind of MR effect. So the only thing I want to emphasize in this slide is that if you believe in the SMR picture, you will already have this the resistance parallel to the current will be larger than the one normal to it. So this one actually, so this value cannot be negative in the standard model. So actually, this kind of a positive SMR has been verified, like confirmed in over 100. Okay, I'm sorry, in more than 100 report. I think I just gave some example here. So also, I think this one is from Felix. But actually, if you look at, sometime we noticed some very strange report. So these guys actually measure this platinum nickel oxide YIG, so which we are very familiar with. So actually, they compare this SMR between standard bilayer and trilayer, and they find that for the bilayer, everything is expected. So it shows a very mild temperature dependence, so nothing really interesting. But they show that in this trilayer device, the MRX is positive at the room temperature, but it goes down all the way with the temperature, but and actually have a sign change here. So you can see it more clearly in the angle dependence measurement. So actually, this is pretty confusing because the SMR is kind of defined to be positive. And actually, the people also show other systematic symmetry measurement and confirm this is SMR, but still it's with a negative sign. And actually, that's very confusing for us. So actually, I want to invite you to look at our previous data of the same structure in spin pumping. Because for the SMR effect, one one condition to it for it to happen is, so the spin current generated by in platinum have to reach YIG to make this effect. But if you look at the temperature dependence of the inverse spin Hall effect, you will find that at very low temperature, the transmission of the spin of this antiferromagnetic system become nearly zero, which means this kind of rational expectation for the SMR at low temperature should be zero, right? You don't have any spin transmission across it, so which means the platinum cannot really feel there is YIG beneath this nickel oxide. So basically, here we should expect a zero SMR, right? But actually, the truth is not like this. So actually, at the very beginning, we are very skeptical. So we measure it by our own samples. So you can see that if you do this field sweeping measurement, you do see some side change here. So because if you look at this 160 Kelvin in the previous slide, there's something here, right? So which means that you still have a lot of spin injection. But somehow, at this temperature, there is no MR, which means it seems that the platinum cannot feel it anymore. But if you go down, it can feel it again, but in a very strange way, give you a negative sign. So this is not so well understood. And if you just do the angle dependence, so it also still tell you that it's really a 4-4 symmetry. It is SMR, but it's negative. So basically, the negative SMR is a fact. We confirm it. So now, actually, we need a kind of an answer to make ourselves kind of can satisfy it. So actually, our way to approach the final kind of solution is to do it pretty systematically. So first, I show this 2 nanometer nickel oxide data like this here. So you can see we have a sign change. So we have been reported by other groups. And if we just gradually increase the thickness of this nickel oxide, so what happens is that you still have this kind of a strange sign change behavior, but the sign change point will increase to the high temperature. But still you have the sign change here. If we further increase the thickness of nickel oxide, okay, that is actually tell you the sign change point dependence. So if we further increase the thickness of nickel oxide to up to 15 nanometer, still you will find that at room temperature, above the room temperature, you cannot see the SMR anymore. But at low temperature, it's still something there. And finally, if you grow this nickel oxide up to 30 nanometer, so it's pretty thick. So actually, the SMR finally vanishes. So it's actually well expected. So you always expect this kind of thing to stop somewhere. But if you compare it with the corresponding spin pumping experiment, so which tells you how the spin transmission in all these kind of samples, you will find something very kind of interesting. So first, there is some good kind of correspondence of this kind of peak position. So basically, we know that here this peak actually means the new temperature, so which means the SMR will be maximized with positive sign around the new temperature. So this is kind of easy to understand. But if you look at this kind of a very thick, relatively thick nickel oxide sample, and pay attention to this green curve is 7 nanometer is something here, and the 15 and the 30 is even beneath it, which means that for this kind of 3 samples, the spin transmission, at least for the low temperature below 200 Kelvin regime, is 0. Nevertheless, you still have finite SMR, right? So actually, this kind of very clearly tell you, even you have the thickness just below, thickness over the value can block any spin transmission, you can still make the SMR to survive a little bit, but finally it will go to 0 when it's 30. So actually, all these kind of things tell us we need a scenario in which SMR can be dominated by nickel oxide only, because you don't need YIG actually. So somehow you don't need YIG. So, but it has to be said that it seems that you need the YIG for the alignment of nickel oxide, but you don't need the YIG to feel the spin transmission through nickel oxide. So actually, so now is our explanation for it. So of course, Felix have tell you yesterday. So we assume this kind of spin flop configuration. So actually, this kind of configuration is very kind of well understood. So when you put an antiferromagnet on your ferromagnet, so a very naive imagination is that it will align collinearly. But if you imagine that, you will find it somehow not correct, because for the antiferromagnet, if you align them collinearly, so the energy somehow will be kind of zero, because you force it to couple like parallel and anti-parallelly. So a good compromise is that if the antiferromagnet new vector can be perpendicular coupled to the ferromagnet, so actually you can have this finite tuning and to further minimize the energy. So actually this kind of thing can be seen in a lot of systems so far. So and then another point is that very important. I think this is also already reflected in Moreno-san's experiment. That is, so you don't need actually. If you only have antiferromagnet system, you can still have SMR, because the SMR effect does not really require a ferromagnet. It just requires that you have a determined axis of the spin. So if it's a bipolar, like the antiferromagnet, so still it should work, right? So combine these two, actually we come up with a kind of explanation for everything. So first, if you will look at the data above the above the new temperature here, so actually there is nothing strange because the new order has not been established. So there is spin transmission, you have positive SMR. So pretty similar to the spin pumping result. Then you just go to lower temperature, lowest temperature in which the new temperature, the nickel oxide will block all the spin transmission. So which means that the spin current can only be felt by the surface of a few layers beneath the platinum, and cannot really see you cannot really feel the spin by itself. But at the same time, if the thickness of nickel oxide is kind of not too large, so this nickel oxide can still rotate coherent by YIG. So actually, YIG here actually serves as some role of a super big magnetic field. So it can actually only control the direction of the nickel oxide. So because the magnetic field is always perpendicular to the new order in nickel oxide on this condition, so actually what you see, the SMR will have a 90-degree phase shift respect to the room temperature result. So this is the origin of so-called negative SMR. So actually, for a fourfold effect like MR, negative sometimes only means 90-degree phase shift. And for
there's no exchange coupling between WPI-AIMR and nickel oxide that makes both the moment parallel to each other?
I think for this case, we believe it's kind of perpendicular. And of course, you can argue maybe it's parallel. But if it's parallel, we don't have this kind of thing. Yeah, but okay, for this kind of thing, I can say, criticize myself like this. If you don't have hard evidence to show this perpendicular, basically everything is just a fantasy, right? So actually, we're preparing single crystalline structure to verify this in the end. Yeah, but so far, my argument is that if with only this kind of possible input, we can reproduce kind of everything.
And in general, if you have a rough interface, you can get this 90-degree coupling with antiferromagnets. They even actually exploit this in GMR stacks in greenheads and hard drives.
So actually, if you look at the temperature, which you have the sign change, so which means that the SMR is 0. So here, what actually happening is that there is competition of this SMR due to YIG, because now you have finite spin transmission, so YIG will automatically give you a positive SMR. But the nickel oxide is still below the new temperature, so it tends to give a negative SMR. So in the end, one positive and one negative, so they will cancel out somewhere. okay, what is very important thing is that this kind of side chain point will actually change with the thickness. With the reason is that if you have a very thin nickel oxide, it's actually will become paramagnet at pretty low temperature. So actually this kind of 0 point of SMR will be kind of a low temperature. So if you make a stronger stronger nickel oxide, so actually this kind of side chain point will shift it to high temperature. So then we have a kind of a systematic understanding of this effect. So low temperature and negative SMR due to this kind of a spin flux coupling. This kind of compensation point due to this kind of competition between positive and negative FMR from YIG and nickel oxide respectively. And above the new temperature or around new temperature, you just have the normal SMR due to YIG. There is no antiferromagnet nickel oxide anymore. So actually, we try to be a little bit quantitatively because we have the theoretical courses, which are also here. So we can make this kind of equation pretty kind of complicated to fit the data just in the first part, just below the new temperature, kind of below the new temperature, and gets the effective numbers of this kind of mixing conductance. So actually, we look at it, we will find that the nickel oxide actually platinum interface is not so bad. And also, I think our experiment also related to Felix' experiment showed yesterday. So actually, yesterday he already pointed out this kind of 90-degree coupling can explain the side chain here. But I want to further point out that it also will explain another factor in his paper. So this is the local measurement of SMR, but this is non-local measurement. So non-local measurement actually requires that you have injection of the spin in one of your channel and travel in the insulator to be picked up in another channel. But if you look at this kind of ion annealed, milled device, so actually this kind of value goes to 0 at low temperature. So that is exactly because the spin current is blocked by the antiferromagnet amorphous YIG at that time. So it's very consistent. Another thing is that we have we know them very well, compete with us. So they actually pretty kind of at the same time produce the same result. So basically, this kind of data tell you the same story, same phenomenon I just showed. But actually, I want to criticize them, and very bravely in front of this camera. Yes. So actually, I think that this kind of a title and the explanation is far from satisfactory. The reason is that they think this effect is due to the spin reflected from this nickel oxide and YIG interface. And very clearly, they say that this is an electric detection of spin backflow from an antiferromagnet insulator and YIG interface, which is obviously not true. Even you don't have to look at my paper, you just look at their paper. Please look at these 2 nanometer and 1 nanometer samples. So they both show a negative SMR at low temperatures. This is nothing wrong. But if this is a backflow from nickel oxide at the low temperature, this effect should be much smaller in 2 nanometer sample than 1 nanometer sample, right? Because you increase the thickness in nickel oxide, you finally will have some kind of a loss of the spin due to the increase of the thickness. So that's something must happen. But they increase the spin, they increase thickness of nickel oxide by like double it, but don't see any increase. But so actually this is very clearly kind of a contradictory to their title. Okay. Yeah, but of course you can. It's I don't. Okay, and what I'm kind of happy is that recently I see a paper put on archive from Professor from Wies, and yeah, of course I personally respect him and I always follow him, right, in my previous research. But actually, he showed that if you have a nickel oxide and a platinum bilayer, and you can see the SMR even in this kind of structure without a YIG, and this is of negative sign. And actually, if you read the paper carefully in this part, actually which shows that he pretty agree with our explanation. But I don't know why he somehow cites the Charlie Chen paper also here. Seems that we have already reached consensus, which I'm not very sure. But anyway, it seems that he agreed, and also important is that people can get SMR only without it, just with the antiferromagnet with platinum. And I think this is also reflected in the story Nakayama-san, Moriyama-san just tell us this morning, right? Okay, the last is I want to thank all the people get involved. So I have a very supportive theoretical team here. Actually, maybe the color here is wrong. Of course, Joe is very happily alive here, and and also thanks Felix, joining halfway of. And also thanks to Dr. Professor Lee, and he teach me a lot about XML, this kind of thing. Yeah, thanks.